Wonderful. I'm so glad to be here, everybody. I'm zooming in from Albuquerque, New Mexico, here in the Engineering and Science Building. I worked with Terry Anderson. She's the engineer, and I'm the linguist on the team. And we discuss sound dimensions and formants. And so to review, or to introduce anyway, we are thinking in terms of sound as a physical phenomena. When you and I talk to each other and we speak over each other, we are blasting sound, we're blasting words into each other's faces at the speed of sound. Sound passes from me to you. And when you talk back, our sound waves pass through each other. Sound has three properties. It is energy, it has frequency, and it has time. And so our research has a basis in mathematics and empirical methods. Formants are defined as energy frequency concentrations. We're all very familiar with the idea of a formant being the product of the fundamental frequency or the pitch, and then it's in harmonics above, in higher harmonics above the fundamental. And so this is actually a very good depiction here on the lower left of a sound wave. A sound wave indeed is a pulse, or it is a twisting kind of a function. And it has, through the center, you have the yellow line would be the fundamental, the green line would be the frequency pitch. This is a pure tone. It would be like a 440 if you played open A on a clarinet, for example. So here's the statement of the problem, is that we need a clearer visualization of formants as defined by Johnson and Fant and Ladefoged and a variety of other researchers. And so I'm using this slide only to show that there are variations in formant. They are irregular. They sometimes come closer, they sometimes diverge, they merge, and they mix in ways. And originally our research, which was begun over 7 years ago, originally our research was designed to determine the energy levels of these formants. And so we said, well, a revised method of formant calculations will display formants and their locations more clearly in the harmonic frequency space. When we look at a diagram, we have the waveform at the top, and then we have the spectrogram on the bottom. And that is a two-dimensional depiction of this three-dimensional object. As sound comes toward you, it is three-dimensional, and because of the energy, it kind of widens. But because of the energy and the shape of sound, it will go around a pole, it will echo. You can talk through a screen, you can talk through a microphone, you can talk through cloth. So it has the ability to propagate and, as it were, maybe heal and reform. So we say that sounds, or the second hypothesis, sounds may be depicted in 3 dimensions using improved technology and innovative methods. The data was analyzed and verified at each step of the process. This is a critical idea. In our approach, we used MATLAB, and we were able to, at each step of the process, look at the data and make sure that our numbers were viable and a reasonable product. A review and practice with current waveform analysis technology showed how formant determination could be improved. Deficits in plotting data were remedied by analysis of numerical bases, mathematical methods, and scaling to optimize data. In essence, we redesigned and we used a physics approach with some friends from the math department. We used a physics approach to describe a physical phenomena. One of the first problems that we had was that formant data for vowels is often reviewed, and it was inconsistent. If you remember the first plot that I showed you, it was inconsistent with the behavior of the formants, and so we tried plotting the formants to determine what was wrong with the data. We would get variations, and formants, because they are at the harmonic bands of the fundamental, should show some kind of regularity. We did a principal component analysis for the t-square values of the histograms, and we found that instead of base 10, which is your counting base, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that they were actually evaluated better in base E. Base E is a log scale, and it looks like a very common product in nature. Base E is a numerical constant, you know, just like pi. So the sound signal was converted into base E instead of base 10, and we found that the data was much more accurate. And so on the plot here, you see we have log base 2, we have log base 10, and we have the natural log of base E. And so it is it was a lucky chance. We kept having trouble fitting the data into a scale. So remember that E is a scale of measurement or a scale of viewing. You want to take it?
Sure. So our next step would be develop an algorithm. We used MATLAB to work the algorithm and go ahead and calculate it. But we found that there were still problems with the data. When you use Fast Fourier Transform, it takes the actual input data from the computer or the microphone and turns it into a digital format. The Fast Fourier Transform introduced time errors and data loss. So we looked for a better kind of transform to go to the frequency space. We found the Chebyshev Transform. So let's go down here to the Chebyshev Transform equation. You can see that it's a differential equation. I'm not going to derive it. No further on that one unless you have questions on it. And it's a pretty straightforward equation. Now let's go down to the Fast Fourier Transform at the bottom. This is where I'm saying that the introduction of the complex numbers is where the problems start. What happens when we deal with complex numbers? We square them, take the square root, or we just throw them away. That's half your data gone. Imaginary numbers or complex numbers are hard to deal with. These aren't introduced with the Chebyshev Transform.
Go ahead and click it. Enter.
You went up one point here. So let's go to step number 4. This is a lot of data. So we needed something that would compile the data into the most important parts of it. Single value decomposition, SVD, is the one that we chose. Now, if you look at one of our matrices that we to the SVD, it's a compilation of, or it's broken down into different components where the important parts are ranked in the S matrix or the singularity matrix. We took that matrix and subtracted it from the original matrix and found that the difference was nearly 0. This allows for representation of the data with a more manageable system telling you what the important components are. And we use this with the Chebyshev Transform, although we have actually gone through with we had a Fast Fourier Transform program as well. The results were very comparable.
Okay, so here's the results. Understanding that sound propagates through space, as I was explaining earlier, it's a impulse through sound, through a medium, through air, and having data for each dimension allows a 3-dimensional depiction of the vowel to be plotted. So we have frequency, we have time, we have energy. This depiction, we say, is more intuitive than a 2-dimensional side view. The difference could be the difference in looking at a train as it passes you versus being in a helicopter and looking down on a train, you know, a moving train, as a product of time and dimension through space. It shows the movement of sound over time. It represents time, frequency, and energy. And when we hit enter, there we go. Thank you. This is a three-dimensional depiction. This is, of course, a highly tentative experimental product, but we have the vowel number 8 on the IPA chart and number 1 on the right. The black rod on the bottom, and I can probably show you with the arrow, is the computer program dealing with 0. And so it creates that. But you notice the distinct shape, and of course we have time going in the upward direction. It has a distinct shape, and each vowel that we plotted, these happen to be from Dr. Ladefoged, each vowel has its own distinctive shape. Here's what we found also that with our data that we produced from MATLAB, is that clean formant banding can be found. Here's love said by first a male and then a female speaker. Mathematical analysis of the formant bands shows that each speaker should have uniqueness of speech and give information that is precise and not depend on interpretation. And so mathematically, we can look on the left side where the male speaker is saying love, and on the right side, and the flat spot in the middle is just the silence. And so this is male, this is female. There are differences that can be mathematically plotted and determined, and so that the difference in intelligibility is obvious. We also found lower frequency bands. Clear formant banding is found in the ranges expected to be generated by the pitch or the fundamental. Male English speaker saying moon. Pitch is also shown as a green line, and you can see it right here on the bottom. This connection of dots is pitch.
Most of your pitch is a calculation. It's not necessarily a measurement. So they take the same data that goes in and they calculate this line.
The upper two levels are above hearing. And you notice here with the dots, we have green dots, we have blue dots, we have yellow dots. What is interesting is that the dots represent formant banding and they do not overlap in any way whatsoever. 4 formant bands are clearly seen here in this example of a female speaker saying moon. Her lower band is higher than the male speaker's than the male speaker's lowest group of formants. So there are distinctions between male and female speakers in terms of pitch, and especially you'll notice in terms of the scale here on the left. Our program automatically produces the banding. Here's what we found. Formants modulate. The formant frequencies vary, but they remain in the frequency band. Male speaker here saying the word fire. The lower band consists of several non-overlapping formant bands. It's interesting that the formants here actually are as part of the pitch signal, and this would be expected knowing that formant should be even number multiples of the fundamental frequency. Here's a male and a female speaker saying the same word. Here's love said by the English speaker, male, and love said by the female. And then here is a common depiction showing exactly the same data. So this on the left is the male, and this is the female speaker. You notice that the pitch moves through the formants, which we saw in the other slide. And then here we have the female formants, and the data, what we're arguing is, of course, is that the data bands on the left are consistent with the harmonics and that the numbers are available for analysis.
So it should be intuitively pointed out or obvious that the pitch can't be above your formants. So our program can definitely handle female voices.
The ability to view process data at each step is a powerful tool for evaluation. The Chebyshev Transform converts data into more usable form without the loss of time. Base E does not force the data to be in a scale that distorts the data. Formants are best evaluated using formant data instead of plotted points. We anticipate changes in the definition of vowel space. We think that improved formant measurements should lead to better voice analysis. Three-dimensional depictions of vowels should show individual sound qualities. And of course, the third point is the most experimental and the most tentative at this point. Here are our email addresses, and we would love to hear from you. And I'll leave with a picture. Here you have the orange fundamental line, and here you have the green harmonics or formants in a three-dimensional depiction. And of course, we have references, and we also have additional sources of research because we did depend heavily on mathematics and the physics of sound. So we'll conclude with that, and thank you very much.
Thank you.
Thank you very much. Any questions, please?
Oh.
Okay, thank you very much. We will move on to our next subject.
Athena, excuse me.
Yes, Professor, yes.
I would like to ask a question or a comment. Well, thank you very much for this presentation. It was a really pleasure for me to attend. And I wish Gunnar Fadner would be with us now. We were good friends for many years in Sweden. Well, if the question is, we would like to have good speech analysis, it is welcome, this research. And it's easy now. It's easier than it used to be. The question is like this. When we produce speech is distorted no matter how clear or how good we speak. So how are you going to have, what do we mean by a good analysis? Do we mean a realistic analysis, although it's not perfect or good or distorted? This is the one point. The other point is that we listen phonetically or linguistically. Most of the times we guess without knowing that we guess. I mean, we think we hear, and in reality it is we guess, we believe we hear something because we know the language. In this case, there is a gap between realistic acoustic analysis and speech analysis within quotation marks. In the last case, we would have a model how speech would be, or what is your opinion about this? I mean, the realistic and the expected. Thank you.
Okay, so may I?
Go ahead.
So when we talk about realistic and expected, you're right. When you listen to something, you're taking a guess at what it is, but it's a form of pattern recognition. I'm going to be honest, completely transparent. I'm not a linguist, I'm an engineer. But by pattern recognition and the same kind of shape, the same kind of almost algorithm that says this is what this looks like, so this is what this sound is the pattern recognition that your brain goes through. Your brain is a very large computer. So any kind of judging, when I talked about the fuzzy analysis, is the same thing. It's the best guess at what we have. So when I listen to a non-native English speaker, I have many different countries represented in my department, I have to stop and think, what did that sound like? That sound, that same shape is what my brain is analyzing. It's what the computer is analyzing. And that is our argument. You can see from the slide that's up here, it's not exact. But remember, on the right is a Nepalese speaker, so it's not as clear. She's got a lovely voice, but I have to stop and think about it. But you see that these are similar. I'm going to point to the right hand of the slide there. There's no way for me to determine the formants because they're all over the place. I can't find a pattern. I can find a pattern in this. That's our argument.
Thank you very much. Thank you. Very interesting. And we would like to listen more from you. I mean to say, as you know, Grandon, you were the other day in our tutorial lecture. I mean, anytime you may present your findings or your work, and you are welcome.
Thank you very much.
Thank you very much indeed. Bye-bye.